So today in class we needed to finish up one-sided derivatives and I felt like we were a bit rushed. So I want to start the video with reviewing one-sided derivatives. So let's start off with the formula. The limit as h goes to 0 from the left side of the function f of x plus h minus f of x all over h, which it looks pretty similar to the right-handed side. Obviously, because it's a limit, we're going to bring the limit in from the right. And this piece right here, oopsie, looks pretty much the same as the definition of a derivative and looks just like the left side. So what are the differences? Well, first of all, you want to remember that this just means y value. And the y value for a function has to be the same y value whether you're using the right side or the left side. A function rule is for every, let's see, x value there is, this is horrible, sorry about my handwriting, exactly one y value. And that's kind of the rule that we're using to help us understand that whichever side you're using, left side or right side, you're still going to have the same one y value. And where the difference is for this piece right here. And I'll do this in red. So this piece right here, and that's not red, use the left function. And then for this one, you're going to use the right function. So that's what we talked about. And then I want to go through that process one more time. So moving over, this was the example I gave you. And if you remember, the first thing I asked you to do was label which side's the left, which side's the right, and which piece you would use to find the y value. And then what we did was we actually found the y value. So y value at x equal to 1. Why are we using x equal to 1? Because if you look right here, that's where the function has a break. If I asked you, are there going to be any other issues with the function? Well, this is a parabola and this is a line. We know that a parabola, we can make a slope anywhere on a parabola and we can make a slope anywhere on the line. Therefore, 1 would be the only place where we're going to have an issue, or we might have an issue. So to start off, I'm going to use the left side of the function to find the y value because of this equal sign. So I get negative 1 squared plus 2, which gives us 1. So the y value of the function is 1. Now, if you remember in class, I said if you want to answer the question, and I'll tell you, for some of you who are a little confused, the question would be, is f of x, or y function, differentiable, meaning does the derivative exist, at, x equal to 1. Alright, so if that's the question, the first step in answering that question will be to check continuity. And how do we check continuity? We check continuity using the three-step process. So what's the three-step process? It is first to find the limit as x approaches 1 from the left side of the function. The next step would be to find the limit as x approaches 1 from the right side of the function. And then the last would be to find f of 1. Well, we already did that. We know that that value is 1. How would I find the left limit? Well, I'm going to use the left side of the function and substitute in 1. Should look familiar. It's how we found the y value. How do you find the right? Same thing. We use the right side of the function and we get 1. So the left side is equal to the right side, which is equal to the y value. And so what that tells us is that f of x is continuous at x equal to 1. And now that we know that the function's continuous, I'm going to have you check differentiability. So we are going to take this question and see, paste it here to actually do the differentiability. Alright, so remember, this was the left side, this was the right side. The y value, f of 1, we found was 1. We used the left side function because of the equal sign. So let's do each of the limits. So this will be the left side, the limit as h goes to 0 from the left of f of, and the x value that we're checking, I'm actually going to write it here, is 1. That's why it says f of 1 plus h minus f of 1 all over h. On the right side, we have the limit as h goes to 0 from the right of f of 1 plus h minus f of 1 all over h. And remember, we have to substitute in the x value right away. We haven't really done this in class. Some of you figured out that you could do it, and yes, you can actually substitute in an x value at the very beginning of the definition if you're trying to find the derivative exactly at an x value. In this case, when you're doing your piecewise, you really want to do that right away. It makes the math easier, it makes things simplify better, and in all honesty, there have been a few problems where I've noticed if you don't do that, the problem doesn't work out well. So it's a little hint to make things easier for you. Substitute in your x value. So next, I need to correctly use the functions to find f of 1 plus h. So I'm going to do a little side note, and I'll do the side note in a gray color. So for the left side function, if I want to find f of 1 plus h, then what I'm going to do is use the left function, negative x squared plus 2. For over here, the right side of the function, if I want to find f of 1 plus h, then I'm going to use the right side function, which is 2x minus 1, and I'm going to do 2. The x is now 1 plus h, and then minus 1. Okay, so I notice I have a little mistake. I forgot the h here. My bad. So going back, it should be negative 1 plus h squared plus 2. Sorry about that. Alright, so now that I have those functions, I'm going to go back into purple for the left side, and I'm going to substitute in what I have there. So where it says f of 1 plus h in purple, I'm actually going to rewrite the function. Negative 1 plus h squared plus 2 minus f of 1. F of 1 was 1. I'm going to put that in brackets just so you understand that where I'm getting that from is up here. We already knew that that was the y value. On the right side in red, we're going to do the limit, see, as h goes to 0 from the right, and we're going to use f of 1 plus h, which is right here, to parentheses 1 plus h minus 1, and then again, and I'm actually going to do this in purple, put a minus sign, f of 1, which is 1, therefore all over h. So just to highlight what's happened, what I did was right here, and right here, I'm using f of 1, which is 1, and that comes from the definition of a derivative. So that's where those y values are coming from. So next piece, oopsie, sorry about that. So the next piece would be to simplify, and this is what we didn't go over in class. So just to make sure that you know what you're doing, I'm going to go through the simplifying process with you. So for this guy, we're going to do the limit as h goes to 0 from the left. Now, right here, the first piece I'm going to do is I'm going to square this guy. So I'm going to have a negative on the outside, 1 plus 2h plus h squared. And then the 2 minus 1 gives me positive 1 in the numerator all over h. And then again, still going, the limit as h goes to 0 from the left. I'm going to distribute my negative. And let's go back to purple then. Negative 1 minus 2h minus h squared plus 1 all over h. You'll notice that the 1's cancel, and I get the limit as h goes to 0 from the left of negative 2h minus h squared over h. You cannot substitute in 0 until you have simplified this enough so that you don't get an undefined in the denominator. So I'm going to factor out an h, and I'm going to get negative 2 minus h in the inside as my factor divided by h. Now they will cancel, and so what I end up with is I'm going to make this h now go to 0, meaning I'm going to physically do the limit, and I get negative 2. So the left side slope, so slope of f of x coming in, sorry about this, from left. Alright, so now we got to do the right. Now I ran out of space, so let's take this guy, all of this. See? Alright. There we go. So all I'm going to do now is simplify the right side. So this side's a little bit easier in terms of simplifying process. So the limit as h goes to 0 from the right hand side, we distribute the 2 plus 2h, minus 1 is minus 2, all over h. Like I said, this one's a little bit simpler. The 2's will cancel. You get the limit as h goes to 0 from the right hand side of 2h over h. Remember I said you simplify completely before you attempt to do the limit. And so now I'm finding the limit as h goes to 0 from the right hand side of 2. The limit of a constant number is itself, so the right side limit is 2. Now if you remember, the left side limit was also 2. Going back a page. Oh, sorry, it was negative 2. So what do we get? We get the limit as h goes to 0 from the left, and I'm just going to call it, let's see, I'm going to actually write out the whole definition so that you see it again. So that was negative 2, but the limit as h goes to 0 from the right hand side of f of x plus h minus f of x all over h is positive 2. Therefore, f prime of 1, where am I getting 1? That was the x value that we talked about at the very beginning, doesn't exist. The derivative doesn't exist because the left side slope, that's this guy, does not equal the right side slope right here. So that's what the one-sided derivatives are. So what I said to you was that I wanted to do an absolute value example. So here we go. When does the derivative fail to exist? Well, just like we said, to start off, when the left side derivative does not equal the right side derivative. You'll hear me talk about corners. And the easiest corner to talk about are absolute value functions. So at the vertex of an absolute value function, you're not going to have a slope exist. And then you heard me talk earlier about discontinuities. All discontinuities, every single one of them, and there are 4 of them. Number 1, a removable. Number 2, a jump. Number 3, an infinite, which is the same as a vertical asymptote. And number 4, an oscillating. Every single one of these, the derivative at those exact points would not exist. Alright, so let's do the absolute value finally. So here's my example. F of x is equal to 2x plus 3. So what you're going to notice is, so actually I decided to change the problem just to simplify a little bit. To talk about absolute value, actually, I'm going to change it one more time. Let's do 1 minus x. So just to make sure we understand what that graph looks like, if you use transformations, you can figure out what the graph does look like. The transformations would say that this is equal to negative parentheses x minus 1. So what does that tell us? This tells me we moved to the right one, but before we did that, we reflect across y-axis. And they actually do go in order. So we would reflect across the y-axis first, and then we would move to the right one. So really what we look like essentially is this guy. So when you reflect across the y-axis, originally you had an absolute value function, pretty much still looks the same. If you have no idea how to draw your absolute value functions, then you will create a table. So my table, I would do, say, -1, and I get the absolute value of 2, which is 2. I put in 0, I get the absolute value of 1, which is 1. I put in 1, and I get the absolute value of 0, which is 0. I put in 2. The absolute value of -1 is +1, so you can see the values are starting to repeat themselves, and you can see what the function looks like. The way that we deal with finding or proving, let's say, that the derivative does not exist at its vertex, you actually create a new function f of x that is a piecewise function. And what pieces are we looking at? We're looking at this guy here. And you should be able to write the equation of that line. The equation of that line would be -x plus 1. And that should actually look familiar because that's exactly what's inside of the absolute value. The right side is a little trickier. Now, if I use the line to continue, there would be the y-intercept. The slope is +1, and the y-intercept is -1. And really what actually happens, and I'll show you in a second, is one of your equations is what is inside the absolute value. That's the blue equation. The other equation is the opposite of what's inside of the absolute value. And so what you see is the pink. Meaning, again, one more time, one of your equations will be exactly what you see, 1 minus x. The other equation will be the opposite of 1 minus x, because that's what's inside of the parentheses, or sorry, the absolute value. Now that you have that, you also have to create the bound. And the domain for the left side would be less than 1. The domain for the right side would be greater than 1. Where do you put the equal sign? Well, it's a continuous function because it's absolute value. You can put it at either of the two. So now that I have that, we are going to set up the one-sided derivative. So remember what we said about setting up for the one-sided derivative. First thing you have to do is check continuity. I would have to do the limit as x goes to 1 from the left, and that would be the left side, which would be -x plus 1, so that would be -1 plus 1, and that gives me 0. I would have to do the limit as x goes to 1 from the right hand side. That would be the second equation, and that would be 1 minus 1, which gives me 0. And then I would also have to find the y value, and the y value would be f of 1. How do I know which one? Well, we knew this was continuous. I understand that. I'm still going through the proof just to make sure. Remember, you look for the one that's equal, and therefore you would be using -x plus 1, which gives us 0. We already knew it was continuous, but I also proved continuity there. Okay? Next piece, I'm going to set up the derivatives. So the limit as h goes to 0 from the left-hand side of f of 1 plus h minus f of 1 all over h. Sorry I keep using 1. I actually didn't mean to do that this time. The right-handed side would be limit as h goes to 0 from the right, and it looks exactly the same, f of 1 plus h minus f of 1 all over h. This problem is a little bit simpler because of what we have for f of 1, but let's go through the limit as h goes to 0 from the left. So for this function here, we're using the left function here. I'm going to come over here to do it. F of 1 plus h would be negative 1 plus h plus 1. And that's what I'm going to put down here. Negative 1 plus h plus 1. The rest of it though, minus f of 1. F of 1 was 0. I'm still writing it there just so you see it. I'm not ignoring it. All over h. And then I'm going to go through and do the right side, which would be, I'll do that in gray I guess, the limit as h goes to 0 from the right hand side. Well, this piece right here, I got to use the right hand side here, which would be f of 1 plus h, sorry that looks horrible, equals 1 plus h, that's the x, minus 1. So I get 1 plus h minus 1, and then right here in purple, I'm going to do minus f of 1. F of 1 was 0. How do I know that? Remember, we found it right here. Alright. And then that whole entire piece, also over h. And then you're just simplifying. So for this guy, we get negative 1 plus 1. Remember that I would also have to distribute the negative right there. So I actually am ending with the limit as h goes to 0 from the left of negative h over h. Simplifies to the limit, as h goes to 0 from the left of negative 1, which is itself negative 1. So there's the slope coming in from the left side. The right function, let me do that, the limit as h goes to 0 from the right hand side, these would cancel. I get h over h, which would be the limit as h goes to 0 from the right hand side of 1, which is itself 1. They are not the same, therefore the derivative at 1 of this piecewise function, which actually is the absolute value function, does not exist. What's nice about the absolute value functions, you know already what the answer is. Now if I asked you what the derivative is for x equal to 2, let's say, so x equal to 2, well, f of x was equal to 1 minus x. And if I ask you to find f prime of 2, you do not need to do a one-sided derivative. Why not? Because, remember, f of x is equal to, and I'm going to go back, copy it over, when I find it, there it is, this guy. So, remember we restated our function as a piecewise function here. So if I'm going to ask you for f prime of 2, and that falls within x greater than 1, you don't need a one-sided derivative. I would only find the derivative using one piece. Therefore, I would do the limit as h goes to 0. Notice I don't have a plus or a minus. I'm literally just going h going to 0 of f of x plus h minus f of x all over h, and I would only use the function x minus 1. Therefore, and I'll do it in one step, f prime of 2 would equal the limit as h goes to 0. This piece right here, f of x plus h, would be the parentheses x plus h, and then minus 1. This minus sign, f of x itself is x minus 1, and then the whole entire piece would be over h. Now, you could actually put in the x equal to 2 right away, meaning this could change to a 2 right away, and this can change to a 2 right away. If that makes the math a little easier for you, you're welcome to do that. In the end, you're only using one piece of the piecewise function because you're not discussing the break of the function. Alright, I think that's everything. This video was a little longer than I had hoped. Hopefully this helps you understand a little bit better the absolute value function. So, real quickly, remember if I give you the absolute value function, this was the original one I was going to start with, then the piecewise function One piece would be the same, and then the other piece would be the opposite of what's inside of the absolute value. How do you know where the break of the function would be? You would have to understand where the vertex would be for the function, and the vertex for this guy would be at positive 3/2. So this is the left side, this is the right side, and then we give the equals to one of the two. Doesn't matter. If you're not sure which side's the left and which side's the right, graph it. This is an absolute value here. Therefore, the left side, ooh, I actually messed up. Duh. And I knew that going into it, which was why I was going to ask you to graph it. Here we go. You see this left side? The left side has the negative slope. That would be this one. See this side? This side has the positive slope. That would be this guy here, and that's the right side. How do I know which one's going to give the equals? You get to pick one. So let me just double check that I did not make that mistake before. Where was I starting for this guy? So that one was fine. Alright. Sorry about that, guys. There it is. So that's how you would write your piecewise function. One more example of writing the piecewise function would be if I did something like -2 absolute value of x minus 4 plus 5, something like that. Alright, so same exact thing. You're going to physically take this guy that's inside the absolute value, and you're just going to make the function once, exactly the same as you see it. And then the other one, you're going to do exactly the way that you see it, except for the inside, right here, you're going to do opposite of x minus 4. And so I'm actually going to simplify that guy a little bit for you. So what do we get? We get -2x. I think that's plus 8 plus 5, which would be plus, I can do math, I swear, 12. 13. There we go. And then you get, this is -2 times -x plus 4. So you get positive 2x minus 8 plus 5, so that's minus 3. Now how do you know which piece is which? Well, first of all, you do have to figure out what x value is going to be your break or the vertex. It's easy to figure it out because inside the absolute value you can set that equal to 0. It works each time. So you get x equal to 4. That's how I know that this one would be 4 and this would be 4. How do you know which symbol to use? If you don't want to graph it, check a value. So what do I mean by that? Use, say, 10 or 0, either side, right? So use 0 in here, and you get -2 times the absolute value of -4 and then plus 5. So the value that we get is -2 times 4 plus 5. And so you end up with positive 3. So what you have to figure out is which one of these, when I substitute in 0, would give me, sorry, -3. It's late. 0 substituted in here gives me -3. Therefore, this is where 0 would be, so this would be less than. That, to me, was probably very confusing to you. So one more time. Either you graph the function, and I'll show you right now. It's shifted to the right 4. 1, 2, 3, 4. It's up 5. 1, 2, 3, 4, 5. And it's upside down because of the -2. So it looks something like this. I'm not going to go through the intercepts because I don't feel like finding them right now, and I hate having inaccurate graphs. So you can tell just by looking at this graph that the left side has a positive slope, and that's the side less than 4. This one has a positive slope, that's less than 4. This side has a negative slope. Here's your negative slope. It's greater than 4. How do I know which one's equal? You get to pick. That's one way to do it. Again, the other way, pick a value. I picked the value of 0. I substitute 0 into the original, and I substitute 0 into each piece, and I figure out which piece gave me the right value, the correct value. 0 is a number less than 4, so that's how I knew that this is less than. Therefore, the other would be the greater than. Now that you have the two pieces, then, if you wanted to do your one-sided derivatives at x equal to 4, you would have the pieces that you need. All right, there you go.